There are two other convergence tests that we should at least mention, the root and ratio test. In both of them, there's a hypothesis that a certain limit needs to exist, and that limit should be less than 1. Many people wonder why less than 1 and not just less than or equal to 1. So as a prelude to that, I want to look at the following two examples. Firstly, I want to look at the sum n equal 1 to infinity 1 over n squared. The term that I'm adding in that goes with index n is naturally 1 over n squared. The next one on the list would be 1 over the square of n plus 1. I want to look at the limit of the ratio of those two things. Writing out the fractions of fractions, simplifying, and then remembering that n plus 1 quantity squared is n squared plus 2n plus 1, it's not difficult to see that the limit is going to be the limit of n squared over n squared plus 2n plus 1. This is a limit of a type that we've seen many times before. There's a polynomial in the numerator, polynomial in the denominator. The degrees are equal. The limit is going to equal the ratio of the lead coefficients, which in this case is equal to 1. So for this particular series, if I look at this limit of the ratio of consecutive terms, I get 1. Also, this particular series converges since it's a p-series with p equal to 2. I want to do the same sort of reasoning for the series sum n equal 1 to infinity 1 over n. In exactly the same way, we figure this limit out to be 1 as well. In the previous example, the limit of consecutive terms came up equal to 1. The series involved converges. In this case, the limit comes up equal to 1, and the series involves diverges. The sum 1 over n is the harmonic series, or if you'd rather think of it this way, it's a p-series with p equal 1. If I calculate this limit of consecutive terms, and it comes up equal to 1, this does not tell me anything about whether my series converges or not, because we might have a case like this, or we might have a case like this. When we talk about the root and ratio test in a moment, there's going to be a limit that I want to exist and be less than 1. I don't want it to be equal to 1, basically because of these two examples we've looked at. The ratio test says when we're thinking about an infinite series, the sum n equal 1 to infinity of an, I'm going to look at the limit of the absolute value of the ratio of two successive terms out of the series. If this limit exists and is less than 1, my original infinite series converges. Not only does it converges in the nice sense of the word, it converges absolutely. If the limit is bigger than 1, it's possible to show that the series diverges. And as we've seen in the previous two examples, if this limit comes up exactly 1, that doesn't tell me convergence or divergence. First thing, I want to convince myself that this statement in front of me is correct. So I'm going to take as my premise the limit as n tends to infinity, absolute of the next term out of the series divided by the one before the term on top is going to be equal to some actual number L, and this number L is strictly less than 1. Because L is strictly less than 1, there's a number a real number between L and 1, pick whatever number is convenient. You could take the number halfway between, or a third of the way from L to 1. Just pick a number and call it R. The statement that the limit is equal to L means that after a while, all of these numbers, absolute value an plus 1 over an, are very close to L. There must be a number R between L and 1, so this R is larger than L is, but it isn't as big as 1. Beyond a certain index, all of the absolute an plus 1s over an have to be close to L. In particular, beyond a certain index, those quantities have to be closer to L than R is, which tells you beyond a certain index, this must be true, so that this must be true, and that this must be true. I'm going to form yet another series. I'm going to start adding up the absolute value of a little n numbers. I'm going to start not at 1 though for the index, but at capital N. Each one of the terms that I'm adding up is less than or equal to R times the preceding term. Using that idea, I can write down some estimates for each one of these terms that I'm adding up in my new series. Not only that, absolute values are at least 0, so these quantities are bounded below by 0 as well. If I could convince myself that the sum of these numbers over on the right converged as I let the terms tend to infinity in number, then that would tell me that the sum of the terms in the middle converge because of the direct comparison test. If I look at some of the indicated partial sums, obviously 0 is less than or equal to absolute A capital N, which is less than or equal to absolute AN. 0 is less than absolute AN plus absolute AN plus 1. AN plus 1 in absolute value is less than or equal to R times absolute AN. So the second partial sum is less than or equal to 1 plus R times a constant. 3 terms is less than absolute AN plus R absolute AN plus R times this term would be R squared absolute AN. 0 less than or equal to the sum of the first 3 terms in my new series is no bigger than 1 plus R squared absolute AN. Obviously, if you had more terms, you would have 1 plus R squared plus R cubed AN, and 1 plus R squared plus R cubed plus R to the 4th AN, and so on and so forth. The AN is a constant. The right-hand sequence of partial sums will converge if 1 plus R squared and so on converges. This is a geometric series. We know when that converges. But in our case, R is positive and R is less than 1, so this is automatically true. These partial sums converge. By the direct comparison test, the partial sums in the middle converge. What we have figured out is this. There's an index, capital N, so that this infinite series converges. This differs from the absolute value version of our original infinite series only because it is lacking absolute A1, absolute A2, out to absolute A number n minus 1. It differs from what we're really talking about by only a finite number of terms. Altering a finite number of terms doesn't change whether the series converges or not. Keeping that in mind, this sum that I'm looking at could be thought of as being an infinite series with index starting at 0, but all of the terms from index 0 to capital N minus 1 are 0. I can alter those numbers to anything I want, and I can say that the resulting series still converges. So, alter the first 0 to the value absolute A1, the second one to absolute A2, and so on out to the finite number of terms absolute AN minus 1. Since we know this converges, and therefore this converges. This tells me that the sum of the absolute values of the ANs converges. That's the definition of the original series converging absolutely. If the R turns out to be larger than 1, a very similar argument will show that the original series diverges. If the limit works out to be exactly 1, then because of the two examples we looked at the beginning, we can't draw any hard conclusion in that case. The remaining test is called the root test. Given an infinite series, I'm going to take its individual terms. If any of them are negative, I get rid of the negative signs by taking absolute value. I look at the index on the term, I take the principal nth root of this, and then I take the limit as n tends to infinity. If this limit exists and is less than 1, the series converges absolutely. If L is bigger than 1, the series diverges, and as with the ratio test, if the L comes up equal to 1, I can't draw a conclusion from this kind of thing. I'm going to look at the case where the limit exists and is less than 1. I at least want to demonstrate that we get absolute convergence. The logic is practically the same as that for the ratio test. I just ask myself, what does this statement mean? It means beyond a certain particular index value, which again we'll call capital N, all of these roots that we're looking at must be close to L. Pick a number R that's between L and 1. In particular, take note that R is less than 1. If I make the index on the root large enough, then these nth root absolute AN quantities must be closer to L than R is. That is to say, on the number line, when the index is beyond some specific fixed index capital N, these roots must be less than R. On the other hand, these principal roots are non-negative because of the absolute value on the AN. Also, the squaring function, the cubing function, the fourth power function, and all such things are increasing as I increase the input. So I can raise each one of these numbers to the nth power without changing the ordering of the results. 0 to the nth power on the left, the nth power of the nth root of absolute AN in the middle, and r raised to the n power on the right. The absolute value of an is trapped between 0 and r raised to the n power. If you imagine adding up such things, you're going to be adding up increasing powers of r to the n. This is a geometric series. Since r is less than 1, it converges. The terms in the middle are trapped between 0 and the terms of a convergent series. This says that the sum of the terms in the middle must converge. Once again, though, altering a finite number of terms doesn't change convergence or divergence, so this tells me that the sum of all of the absolute ANs converge. Just as with the ratio test, this is what it means for the original series to converge absolutely, so this demonstration is finished. As a quick example, let's see if this infinite series converges or not, using the ratio test. Figure out what terms go with a given index, index n, and index n plus 1. When I calculate the limit as n tends to infinity, absolute an plus 1 over an, I write the fractions in. All numbers inside the absolute value symbols are positive, which means I can just drop the absolute value symbols. Turn the fraction on the bottom upside down. I have one more factor of 3 upstairs than downstairs, so 1 survives. N factorial is the product of n and n minus 1, and so on, all the way down to 1. N plus 1 factorial is n plus 1 times n minus 1 down to 1. The only factors that don't cancel out would be the n plus 1 on the bottom. As n tends to infinity, 3 divided by n plus 1 becomes arbitrarily small, so the limit is 0. The limit is 0, which is less than 1. This series converges absolutely. Typically, when all factors are raised to the power of the index on the term, or something related to that index in a simple way, that's the signal that you should probably use the root test instead. So I want to look at the sum n equal 1 to infinity, negative 1 to the n plus 1 power multiplied by 3 to the n divided by n to the n. When I take the absolute value, this just removes any influence of that negative 1 to the n plus 1 power factor. 3 to the n over n to the n is the nth power of 3 over n. The nth root of that is 3 divided by n. This number tends to 0 as n tends to infinity. 0 is less than 1. The root test tells me that my infinite series converges absolutely. It converges, and it converges in the nice way in which I could rearrange it in any fashion that I wanted to.